Good evening, students. I'll wait for a minute or two for the others to join.
Yes, ma'am.
Okay. Uh, okay. Good evening, students. Let's start the class for the day. In the last class, we were discussing about the parameters. Before that, just give me the confirmation if you can hear me clearly and see the screen. Good evening, students. Let us start the class now. In the bond parameters, one of them was and we discussed something about it. Ordered a few. I'm just waiting.
Sorry, ma'am, I have network issues, so I left.
Good evening, students. Can you hear me and see the screen?
Yes, ma'am.
Okay. So in the last class, we were talking about the bond parameters, and one of them was resonance structures. So now let us move further. First, we will recall what we did. I stated you a fact that benzene is one of the, or rather the parent hydrocarbon of parent hydrocarbon, and it has got alternate double or triple bond. As you can see on my screen, that benzene is a 6-carbon atom compound in which there are alternate single and double bonds between carbon atoms, right? Now, we know, or I have told you that in the last class that the compounds which contain either carbon-carbon double or carbon-carbon triple bond decolorize alkaline KMnO4, which is commonly known as Bayer's reagent. More details of this particular thing will be taught to you in the chapter of hydrocarbons. But we must understand one fact that benzene, although it has 3 carbon-carbon double bond, it does not decolorize Bayer's reagent. Now, these are two contradictory things. It was expected to do so, but it is not doing so. So what do we say, or how to solve this puzzle? What scientists did was, they said that the scientists said that the real structure of benzene is not any one of them, right? He said, we can draw benzene in the structures as shown on the screen. There, I have shown you 2 structures of benzene in which you can see the double bond between carbon atoms are at different position. Such structures are called as canonical forms or canonical structures. Then what is the real structure of benzene? The real structure of benzene will be in between them, right? That is one which is drawn on the extreme right hand side and labeled as resonance hybrid. Is it clear? That benzene was having 2 structures, is supposed to have 2 structures which are represented as canonical forms, and the real structure of benzene will be its resonance hybrid, right? So what we say is, we define and we describe resonance as a phenomenon when all the properties of a substance or a compound are not described or cannot be described by assuming one structure, we assume and we say that the compound is having a structure in between whatever possible structures are. And such structures are called as canonical structures, and the ultimate structure which we use to represent it is known as resonance hybrid. I hope it is clear. When we say that one specific structure, like till now, you were saying you were having a specific structure related things. We said that methane has sp3 hybridization, water has bent geometry, so that were fixed. And in the cases of both methane and water, the structures and properties were matching. In this case, since structure and properties are not matching, we said it is a mixture of more than one thing, right? See, I am putting more time and effort into resonance structure is because the chapter of hydrocarbon has the details of this, right? So if we know the basics right now, it will be easier for you to understand that part. I believe it is clear to you. If not, please raise your query. Now, when we describe resonance, it is important to say that energies of canonical forms are similar, not identical. Remember that they are similar. Position of nuclei are similar. Bonding and non-bonding pairs of electrons are same, right? That is important. You cannot have a different number of proton, electron, and neutrons in different canonical forms. Moving on to the structure of resonance, as shown by the ozone. As you can see, ozone is said to be resonance hybrid of structure number 1 and structure number 2. Look carefully, you will notice that one of the oxygen is having a double bond and one of the oxygen is having a single bond. Their bond lengths are different. One is 148 picometer for single bond and 121 picometer for the double bond, right? Whereas the last one is resonance hybrid. In resonance hybrid, what do you see? The bond length is 128 picometer, which is in between 121 and 148. So that is what we meant when we said that the properties of ozone cannot be described by assuming a single structure, right? We say it is having two structures or more than two structures in some cases. In benzene, we have total of 6 structures. Now, if you look at this is called as a double-headed arrow, which indicates that one form is, there are two different forms of ozone. And this is the resonance hybrid of ozone, right? Now, these are the certain facts which we must remember in order to explain the resonance, right? The first stabilizes the molecule. Please remember this key sentence from my side, that resonance and stability now onwards have to be synonyms, right? Whenever there is a term comes resonance, believe me, you have to understand without saying it is stable. If I talk about the organic chemistry, we say benzene is resonance stabilized. This will solve many of your questions and queries in class 11th as well as class 12. So please remember, resonance and stability are the synonyms, right? So because of the resonance, a molecule becomes stable because the energy of resonance hybrid is less than the energy of any of the canonical structure. Let me explain this point to you. This means that, or you must have experience in your day-to-day life, that resonance, or rather let us take an example from day-to-day life. Less stable, less energy means less reactivity, right? So what happens here is we are trying to establish one fact, that resonance hybrid is having a lesser amount of energy than any of the canonical forms. So let's go back to the structures of benzene and assign certain energy to it. Now, if I say the energy of this structure is 120 kilojoules, and let's say it is having 130 kilojoules, the energy of this resonance hybrid will be 110 kilojoules. Please don't quote it anywhere. These are just hypothetical numbers to explain the concept, right? That the energy of resonance hybrid is less than either of the canonical forms' energy. It means it must be less reactive. You must have seen in your day-to-day life, when you have fever, you can't work as efficiently as you can do it in a normal day, right? So that is the first point, that energy of any of the canonical form is always going to be more than the resonance hybrid. The second point is resonance averages the bond characteristics as a whole, right? And the next one is the canonical forms have no real existence. That means we believe them to exist. They are actually not existing. Resonance averages the bond characteristics as a whole, that I have told you with the example of ozone, where they were having two different bond lengths. Let's go back to ozone and see. They were having different bond lengths as 121 picometer and 148 picometers. And in reality, in the resonance hybrid, all the bond lengths, let that be double bond, let that be the single bond, it's only 128 picometer, right? So I believe these 3 points are clear with reference to resonance, right? Now, then we say the molecules does not exist for a certain fraction of a time in one canonical form and for other fraction of time in other canonical form. There is no such equilibrium. That means we are saying that once they are existing in a particular form, if I look at the structure of benzene, if some molecules are existing in one form, they will keep on, once the equilibrium is established, once the resonance is stabilized, right? They are not going to change their contributions, right? So as such, we say it is resonance hybrid. Then these are the structures of carbonate ion. Please note them out, right? Do you understand, or have you understood these structures? They are the most frequent: ozone and carbon dioxide, ozone and carbonate ion. These are very frequently asked in exam. You are asked to write their structures. Do you understand these structures? Ritika, do you understand these structures?
Yes, ma'am.
Okay. Now, this is the resonance hybrid I have shown you. If you understand it, I have shown you. Now, what will be the charge on the structure number 1, 2, and 3? structure number 1, 2, and 3, will they have charge or not? If yes, then what? Yeah, can you tell me the charge on structure number 1, 2, and 3? There is a common mistake which I usually find in your question answer copies is that students put a negative charge if I'm redrawing the structure number 1. They put 2 negative charges here and 2 negative charges here also. That is incorrect, right? You have to draw, as in this image, you have to draw the negative charge either at the 2 oxygen atoms or as on an overall molecule, right? In NCERT, they have not drawn it on individual atom, they had drawn it on a overall molecule. So please, remember this one is incorrect. Whenever you are drawing them or you are making a choice that one of the canonical structure of carbonate and iron is, please make sure that you choose the correct option. Is it clear, Shweta?
Yes, ma'am.
Okay. Now, have you heard about this term polarity of bonds? Ananya, what do you understand by this term polarity of bonds?
Mom, I haven't learned this.
Okay, this is not done in your school, Ananya.
No, Mom.
Okay. Shweta and Ritika?
Mom, they have just started this lesson in my school.
Okay. So, can you one by one, Ritika, which lesson is going on in your school?
Mom, they have just started with the chemical bonding.
Okay. And Shweta, you?
Well, 1 second, wait.
Ananya, which chapter is going on in your school?
One second, Mom, I'm checking.
Okay.
Ma'am, from volume 2, she started redox reaction.
I didn't get you, Shweta.
Mom, she's actually done with the second, third, fourth chapter, and then she also finished the redox reaction chapter. Now she's starting with some basic concepts of chemistry.
So there are 2 chapters. Some basic concepts of chemistry is first chapter, and book 2, the second last chapter is again based on basic techniques or organic chemistry basic concepts. No issues. Let's move on. So please remember, now onwards, this becomes a key outcome. Till now, we understood the bonds are either purely covalent or purely ionic. Right? You say that sodium chloride forms, there exists a ionic bond between sodium ion and chloride ion. That is sodium chloride is an ionic compound, right? But that is the reality, that every covalent bond has an ionic character. A certain part of it has an ionic character, which is measured by dipole moment. Fajans, please note it down in your minds as well as in your copies, that every covalent bond has a certain ionic character, which we can measure with the help of dipole moment. Similarly, ionic bond has a covalent character, which is measured by Fajans rule. You get many questions on these concepts. They seem very small, very simple. So first, we will take on understand what is a dipole moment. This must be familiar to you because at the beginning of the chapter, we did polar covalent and non-polar will have a non-polar covalent bond. Cl2, H2, F, non-polar covalent bond. In case of H2, it has two hydrogen bonds sharing a pair of two hydrogen atoms sharing a pair of electron, right? Both of them have equal power, so it will be lying between them. Or we said the shared pair of electrons lie closer to chlorine or a fluorine, which is more electronegative as compared to hydrogen. It will get a partial negative or it will get a partial positive charge. The value of this partial, or we call it as delta, is always less than 1. Right? So how much polar a covalent bond is, let's find it out with the help of dipole moment. We define dipole moment, as you can see, one of the poles, that is the poles, that is bond length. Now, charge on any of the atoms means that if in case of H plus, it is 0 plus 0.37. In this case, in case of chlorine, it will be minus 0.37. So you have to take only the numerical value of charge, right? And then you have to multiply it by distance, and that is bond length, to get the value of a dipole moment. That's how with this alphabet, I believe you know, this alphabet is called as mu. Right? You can say it MEU, or maybe you can say it as ME. This is mu. Mu is equal to E into D. Then the unit of dipole moment is debye. And 1 bi will be equal to 3.33 into 10 to the power minus 3 coulombic meters, or 1 into 10 to the power minus 18 ESU dot centimeter. Please be careful with units when you are solving the problems. There are hardly any problems, although, and a simple and a direct one. Now, how do we represent dipole moment? Dipole moment is a vector quantity. I believe you must have been taught by your physics faculty, vector and scalar. The quantities are of two types, vector quantities and scalar quantities. The vector quantities have a direction, right? And they are represented by a small arrow, in which, see, if I have HF, I will draw the arrow, right? It will be, the head of the arrow will be pointing towards a negative center, and at the tail, what you make? You make a positive charge like this, right? I refer to it as a positive charge. Is it clear to you, Shweta?
Yes.
Now, if I have to talk about the dipole moment in a polyatomic molecule, vector addition, vector subtraction must have been taught to you in physics, right? Taking the advantage or taking that learning, if I have to find the dipole moment of water molecule. So what we will do? Oxygen is more electronegative. So we will draw this arrow, right? And we will draw this arrow. The head pointing towards the electronegative element and hydrogen being electropositive. The vector move, the net resultant dipole will be in between these two, and this one will be our resultant dipole, right? So that means we say water is a polar molecule. If the net dipole moment, please remember, for polyatomic molecules, we say net dipole moment. What happens to net dipole moment? If it is 0, then that means the compound is non-polar. But if you get something like you are getting in case of water, then you know the bond is, or the molecule is polar, right? Let's take some more example, understand few more example. You can see in BF3, does it have a total dipole moment or not? Quickly. I have drawn all the images for you. Any answer? Ananya, what will be the dipole moment of BF3?
Mom, 1 minute now.
Okay. Remember in the last class or before that, we did the structure of BF3 as triangular planar. This is one BF bond, this is the second one, this is the third one, right? The resultant of this one dipole will be this, another dipole will be this. They have the same bond length, they have the same values. So that means what? They are going to, the resultant will be in between these two, right? And that of BF3, last BF bond is like that. Can you see both of them are cancelling each other? This one and this one. Or in this image, which is drawn on the left-hand side of my screen, look at this and look at this. The resultant of this BF bond and this BF bond is in between these two. That is this one and this one. You will notice they are in opposite direction and magnitude is same. So the total dipole moment of this molecule will become 0. Is it clear to all of you, Ritika, Shweta, and Ananya?
Yes, ma'am.
If it is taking you to take some time, please go back to the VSCPR theory wala topic. There we discuss the geometries of the molecule.
Excuse you,
Now, if
ma'am.
yeah,
Can you please repeat that concept once more?
before that, I don't know who said that. Please say it again. I just want to know whether you have done vectors in your class or not.
Yes, ma'am, we have.
Physics class, not you. You have done, right?
Yes, ma'am.
Okay. This part is not clear to you. You want me to repeat this one?
Yeah.
Okay. I'm explaining it step by step. Then please check me out and tell me that which step you are not able to follow or not get that one. This is BF3 molecule. We done in the VSEPR. It has got three electrons in the valence shell. Its shape is trigonal planar, right? So if I draw the vector of it, if it is not clear, if I have to draw it for BeCl2, let's take a much more simpler molecule. For BeCl2, the dipole will be in this way. Chlorine is electronegative as compared to beryllium. It will have a positive end. Similarly, BeCl2, in this direction, it will be opposite. If you do the vector sum of it, the net resultant will be 0. Is it clear to all of you? The example of BeCl2 or carbon dioxide made below it. Is it clear to all of you?
Yes, now it's clear.
Okay. Now, moving on to the BF3 one. BF3, it is slightly more complicated than that. BF3, we say, okay, let me write F also. The result, it will be having one dipole like this, another dipole like this. The resultant of these two, this one and this one, will be somewhere in between them, or rather exactly in between them in this direction. And what about the third BF3 wala dipole? It will be like this. If I draw it here, you will realize that this one and this one, they will cancel out each other and the net dipole moment will become 0. Is it clear to all of you now?
Yes, ma'am.
Okay.
Mom, can you go back to, yeah, yes, ma'am. No, the next slide.
Yeah. Any queries in the slide?
No, ma'am.
Okay. Here I have taken another example of BeCl2, BF3, right? Can I move further?
Yes, ma'am. Thank you.
Okay. Now, I have an interesting question for you, which is explained in NCERT also. Let me put it on a separate slide because answer is visible on this one. See, you have NH3 and NF3. If I talk in terms of hybridization, you will say both of them are going to have the same hybridization and same structure, isn't it? NH3, if you remember, we said nitrogen was having a lone pair of electrons. Cases 7 degree, and we said it has got a distorted geometry. Right? Now the question is, what about their dipole moment? The dipole moment will be equal or not. And then why? Just think quickly, Ritika, Shweta, and Ananya. This is one of the most asked reasoning question from this particular chapter. It's there in NCERT also, no doubt about it. Any idea, or should I explain, Shweta? Now, here is the answer to this question. Between nitrogen and hydrogen, you have to understand this problem, or you have to approach to the dipole moment question, that you must understand which is more electronegative or which is more electropositive. Between nitrogen and hydrogen, nitrogen is more electronegative. Right? Similarly, between nitrogen and fluorine, which is more electronegative? We'll say fluorine is more electronegative. So that means what will be the direction in case of ammonia? As we have understood that nitrogen is more electronegative, negative end will have an arrow and the positive end will have a positive charge, right? So that means the net resultant of these will be these 1, 2, and 3 will be in the same direction, that is in this direction, right? Similarly, the lone pair will always be having a resultant in this direction. That means both of these dipoles are going to add each other and giving it a larger dipole moment. If I talk about NF3, what happens here is that fluorine is more electronegative than nitrogen. Again, the knowledge of periodic table or understanding of periodic table becomes handy and important in this case, right? So fluorine will be more electronegative. Therefore, the dipoles will be drawn like this. And their resultant, as you know, their resultant will be in between them in this direction. So this will be in this direction. Dipole moment due to lone pair of electrons will be in this direction. As you can see, they are going to cancel out each other to an extent, maybe 70% or 80%. So the overall value is going to be less. So that means the dipole moment of ammonia will be more than that of NF3. Is it making sense to you, Shweta? Ritika, do you understand it?
Yes, ma'am.
Okay, if you want to note it down, I have put it in a simpler form. Fluorine is more electronegative than hydrogen. It is expected that the net dipole moment of ammonia is greater than ammonia. Right? The key sentence is written in the board. Resultant moment, yeah, resultant dipole moment of NH bond adds up to the bond moment of lone pair. Whereas in case of NF bonds, it cancels out. That is the key and the precise answer which you must give to the examiner in order to get 2 marks. It's usually a 2 marks reasoning question. Maybe 3 marks if they want you to decide it. For deciding which is having greater is 1 mark. For writing the explanation, it will be of again 2 marks, making it a 3 mark question. Now, let's solve this question. Which of the following molecule or molecules will have 0 dipole moment? I'm giving you 3 minutes from my side. Please find it out quickly. Hmm. 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 See, for the convenience of the students, I just displayed the answer for you. That if anything is having a regular geometry, the vector sum will become 0. You know that CO2 has a linear structure. CCl4 will have CO2 we have discussed. It has got linear. CCl4 is having like similar CH4 like structure, that is tetrahedral. BF3 we know it is having a triangular planar. BF2 is having a linear structure. In case of CHCl3 and NH3, we will have a net dipole moment. You know, ammonia has a distorted structure because of the presence of one lone pair of electrons. But what is the reason for CHCl3? Let me explain it to you. In case of CHCl3, the structure is like this. One is a CH bond, the other three are CCl bonds. Two CCl bonds will have a resultant. Similarly, their resultant, if matched with the other CCl bond, it will again have a resultant, and that CH bond will not be able to cancel out. Had it been CH2Cl2, of course, which is a part of next question, that will have the resultants will cancel out. As you can draw them as like this. This is H, Cl, Cl. The resultant of CCl bonds will be in between them, and that of CH bond will be in between them. That will approximately cancel it out, right? At some places, different atoms are going to give you the net resultant. The best way to understand or having a generalization about it is that the compounds with the regular geometries have 0 net dipole moment. That is important for you to understand. CHCl3 will in I just missed out on water again has 2 lone pair and 2 bond pair. So that will also have a distorted geometry. Hence, it will have a net dipole moment. Is it clear to you, Ritika, Shweta, and Ananya?
Yes, yes.
Okay. Now, this question. Write the decreasing order of dipole moment among CH3Cl, CH2Cl2, CHCl3. Let's take a minute to solve this. You just have to understand which dipole is going to cancel each other. If not completely, then partially. See, here is the answer. CH3Cl will have highest dipole moment, followed by CH2Cl2 and followed by CHCl3. Please look at it carefully and critically, think logically, and you can solve it at your own. Once you do some practice on the shapes of the molecule and then you do these type of questions, then you will be easily able to do it. And please revert back to me whenever you are done with this topic at your own end, because in the test, I'm going to give you the questions. Mostly, this concept will have at least 1 or 2 questions. They are important because you don't have to do calculation, but you still have to apply the concept. Is it clear to all of you?
Yes, ma'am.
Okay, this one should be very easy. Polar covalent bond, no calculation, nothing. Yeah, Ritika, what's the answer? Let's solve it then, if you feel it's that difficult. Electronegativity, just think about it. There are 2 oxygen, 2 nitrogen, 2 fluorine, 1 hydrogen, 1 chlorine. Both of them have equal tendency to attract the shared pair of electron. Bond pair will remain in between 2 oxygen atoms. Similarly, in this case, it will remain between two atoms. Between fluorine, it will remain between 2. For HCl, it will lie closer to chlorine. So now what's the answer, Ritika? Ananya, your answer is?
Is it HCl?
Right. Is there still any doubt in the concepts of polar and non-polar covalent bonds? Shweta, do you have any doubt in the answer, or is something which is not so clear for polar covalent and polar
No, ma'am.
non-polar? But then what took you so long to answer the question?
She's confused.
Okay, it seems that last week was full of your exams and maybe some of you are still having your exams. But this weekend, please find some time, or maybe before the next class on Wednesday, please find some time. Revise the concepts of chemical bonding. They are interesting, as well as one related to other one. If you do them systematically one after the other, you'll be able to grasp them and you will be able to score more. Now the last one. This is the last one for this. This is the correct statement. Mu, as I told you, is a symbol of dipole moment. I think we have discussed all of the molecules here just now. Take a deep breath, spend 2 minutes. You should be able to have an answer. Okay, let's start doing NH3 is more than ammonia. Is it correct or not, Ananya? We just discuss it. We discussed in some previous slides that in case of ammonia, the resultant dipole moment will be like this and the lone pair will be like this. They will add up. Whereas in case of NF3, the resultant of these
Mom.
three, yeah,
Mom, it's what is correct this one?
I didn't get you, Ananya, what you said. Please repeat.
Mom, I said this statement is true.
I'm still not too sure what you said, Ananya. Please be a bit louder.
Mom,
I'm waiting for your response, Ananya.
the statement is false.
I'm so sorry, I cannot understand what you are saying, but I'm still trying to
Statement is
explain what I have.
false. The statement
If you are
is
saying
false.
all of the above,
The first statement is false.
first statement is false. How? See, we discussed the same thing a moment
Of
ago.
the dipole moment is of NH3 is greater than NH3. Oh,
The dipole moment of I'm sorry for the interruption. We had a certain connectivity issues here. Let's resume from the point from where we left. See, we were discussing this particular problem. Am I audible and visible to all of you?
Yes, ma'am.
Okay, so we were doing this particular problem where we discussed that which one is we wanted to find the answer, which one is the correct one. I believe the first option is clear to all of you. This is correct. We have discussed the same just a minute ago, right? The second one, BF3. BF3 is having a regular geometry. Therefore, BF3 will have a net dipole moment as 0. CO2 we have discussed. Similarly, we have discussed CCl4 also, right? So therefore, all the options are correct. So this was all about finding an ionic character in a covalent bond with the help of dipole moment. Moving on, we will learn about how to find the covalent character in ionic bond. Now that can be done with the help of Pajan's rule. Okay, I'm sorry again for the interruption. Let us start again. We'll begin with the Fajans rule now, which is used for finding the covalent character I hope everything is clear to you now all. Let us quickly make up for the lost time. As I told you that Fajan, no bond in nature is either going to be 100% ionic or 100% covalent. Talking about the Fajan's rule, it is used for predicting the nature of covalent character in an ionic bond, right? So there are certain things or certain points which we must understand and learn one by one, that what are the rules for finding such things, right? So look at the third point on the slide carefully. The polarizing power of cation. What is the meaning of that? We have a cation cloud like this, and let's say we have a anion cloud like this. When this cation, which is positively charged, approaches towards the negatively charged anion, it starts moving in this direction, right? So what happens? The polarizing power of the cation, the polarizability of the ion. This ionic negatively charged cloud starts moving in this direction. It distorts, right? And the cation is attracted towards it. So we say that every cation possesses a polarizing power, right? And every anion possesses polarizability. So whenever a cation and anion approach each other, this cloud, as you can see, this electron cloud of anion is distorted, right? And which causes the covalent character to be developed in an ionic compound. That means in ionic compound, we were saying that electrons are confined to the cation and anion in their respective areas. Cation having one electron less, anion having one electron more than the respective cation at least. In case of, for example, sodium chloride. In sodium oxide, it will be 2 each, right? So as you can see, the electron cloud of anion, instead of being its own defined area, it is spreading. We call it as the distortion of the or polarization of the cloud. It becomes more of a sharing, not defined or put in their own shells, but they are now being shared between two, right? So they have given us certain rules which we must remember to decide and solve the questions related to it. The first rule says, with the increase in the cationic size, ionic nature of the bond increases, right? I have highlighted this one first point, that with increase in, that means between lithium, sodium, potassium, larger the size of the cation, more will be the ionic character. And the vice versa is also true. Smaller the size of cation, more will be the covalent character in an ionic compound, right? So both the statements are here for you. You must remember them, right? That how does the polarization of ionic bond changes with the size of the cation and anion. Is it clear to you, Shweta?
Yes, ma'am.
Okay, everyone else is also clear, I believe. Let's move on. Now we are talking with reference to the size of anion. For the size of anion, we say smaller the size of anion, more will be the ionic nature or ionic character in the bond, right?
The flip side of it or the opposite of it is that larger the size of anion, more will be the covalent character, right? Then in the last point, we have compared the different charges on the cations. You know that sodium is a unipositive cation, magnesium is a dipositive, aluminum is a tripositive, and silicon is a tripositive cation, right? Greater the charge on the cation, greater will be the covalent character. So that means silicon tetrachloride will be covalent and NaCl will be more ionic, right? Now, let's understand it for the, what is the meaning of a pseudo-inert gas configuration? Now, pseudo-inert gas configuration applies to D block elements, right? D block elements in which we are concerned or we talk about the electron being added to the penultimate orbital in n-1 d level. So they are said to be having a pseudo-inert gas configuration. On the other hand, we are having the atoms which are, or ions, which are having actual inert gas configuration. That means we can say S and P block elements can have an inert gas configuration for sure. So the rule says that cation with the exact inert gas configuration will be more ionic, while the cation with pseudo inert gas configuration will be more covalent. Copper, being a D block element, will form a more covalent compound as compared to sodium. Now we will do some multiple choice questions so as to check our learning. I specifically have put the question which I wanted to ask in red color so as to avoid any confusion in the answer, right? Because everything is opposite of each other. So ionic nature of a bond is lowest in calcium. I have deliberately kept the cation same. So what's the answer? What's your answer, Ritika? Ananya, what's your answer?
Ma'am, it's
Okay.
option A.
Option A. Okay, let's check. That is correct. I have given the explanation because at times these are opposite of each other and they become a bit confused. And therefore, I have written both the explanation. That is, smaller the size of an ion, more will be the ionic character of bond. Then if I have asked for the highest ionic character, then the answer would have been calcium fluoride. Okay, let's see another question. Ionic nature is highest in. It is opposite of that. So quickly you can answer me. I think you need to find the smallest anion. So Ritika, what will be your answer?
Ma'am, option A.
Ionic nature is highest in option A, right? Have I heard correct, Ritika?
Yes, ma'am.
Okay. It should be, see, I'm still not too sure. I'm so sorry for that. That whether you said silver chloride or silver fluoride, it cannot be silver chloride. It's in between. Even if I have a confusion, so I should either be going for AgF or AgI. Please develop a correlation in your minds. I probably learn it that smaller the size of anion. Anion begins with A, right? So I correlated to the initials of my name, Shikha, and anion and more ionic. Somehow I manage like that. So you also can develop some of your tricks and tips to find the answer of such a questions which are very confusing at times, but probably easy to score, right? Now, this part of the chapter, theories based on quantum mechanics. We have done it. This chapter is, I'll say, it has ups and highs. You don't know what to teach first and what to teach at the end. So let's recall and what we have done and what we still need to add to the things. So basically, why do we need a quantum mechanic approach to the chemical bonding? They say that Lewis structure was the first thing. The Lewis approach was the first thing. It was not, it helps us in writing the structure of molecules, but it does not tell us about the shapes of the polyatomic molecules. As we have done it now, that ammonia will be, let's say, distorted or pyramidal, water will be bent, like that, right? It does not give that why the bond length of certain molecules are different and why certain molecules may be almost similar. So to overcome these things, we have a VB, that is valence bond theory, and molecular orbital theory. Remember, VSEPR is not quantitative. It just tells it will have a repulsive force more or attractive force more. It will tell that. As remember, I told you that bond angle, it's a rough estimation, decreases by approximately 2.5 degrees, right? But that's not a quantitative aspect of it. They have not specified. That we have observed it and then we have told you like that, right? So we talked about, then we need to talk about valence bond theory and molecular orbital theory. Molecular orbital theory, by now, we might not have done in under 1, 2, 3, 4 steps, but I'm pretty sure that we are thorough with it. That a covalent bond will be formed only when the two orbitals have two half-filled orbitals, that is having 1 electron each of opposite spin, right? This is the first and the focus point of the VBT or valence bond theory. As you know, that overlap will be in the opposite direction, nucleus will be in the center. This all we have done. Then we have done about, we have understood what are the sigma and pi bonds and how they are formed. Do you agree with me that we have done this section already? Ritika, have we done it or not?
We have done it, ma'am.
Okay. Now this is the only section which I just, when I confirmed with the NCERT, I just found that we have not dealt with these two images. You will notice that I believe in putting the images directly from NCERT. The reason being, I expect them to be asked and as per NEP guidelines. Look at the first picture on the left-hand side of my screen. That we have two atoms of hydrogen, one named as HA, another named as HB, right? So they have shown us that what are the old forces and what are the new forces which have developed during the formation of H2 molecule. The old forces means that which are represented by the dotted lines. That proton of one atom is attracting the electron of another atom. This is in both the cases. Proton of HA atom is attracting the electron of A atom. Similarly, proton of HB, the second atom, is attracting the electron of the second atom. Now, when they are coming closer to each other and trying to form the bond, what happens? New attractive forces develop. They have showed them with the solid lines that HA atom's proton and HB atom's electron are going to attract each other. Similarly, the proton of HB atom is going to attract the electron of HA atom. That is about the attractive forces. We are two more new attractive forces are being developed between proton of one atom and electron of another atom. Similarly, the repulsive forces are now repulsive forces were not there earlier in the atoms. When they are coming closer to form the molecule, repulsive forces are also developing. That is, the protons of both atoms A and B are going to repel each other. Similarly, the electrons of both the atoms A and B are going to repel each other. Now coming to the next image, this one, where we can see that there are two hydrogen atoms. This was the first and the second atom. Now what they are doing, they're coming closer, you can see. Right? At this place, they are coming closer. And in this place, they are half overlapping each other. Right? In this image, the bond length corresponding to this is 74 picometers because it is an internuclear distance. Internuclear distance at which the sum total of new attractive forces is more than repulsive forces. Attractive forces are say 100 units, repulsive forces are let's say 40 units. So attractives are more, that means a molecule will be formed by the overlap, right? Similarly, the energy corresponding to this is 435.8 kilojoules per mole. So that means when the two atoms of hydrogen are coming closer to each other, there will be a point where the attractive force is highest, and that point is referred as bond length, and the energy corresponding to it is called as bond energy, right? And please remember, I expect this, maybe I can creatively put this image in front of you in your paper and ask question, find the bond length, find the bond energy, what is the distance of the closest approach, at what time the atoms are at maximum distance from each other, right? Now, next topic we have to begin with is molecular orbital theory. I'll just take a moment because we have just lost some time. This molecule to tell you certain facts about MOT. In short form, we call it as MOT, molecular orbital theory. Till now, whatever we have discussed and done is called as atomic orbitals, right? Now, when a molecule is formed, we say that existence of atom is over. Atom does not exist now, right? Now, when atom does not exist, that means molecule will also not exist, right? Is it clear to all of you? That in molecular theory, we will be talking about the molecular orbital. Some of the rules which we have understood in atomic orbital theories, which is VBT, VSEPR, all of them will apply to it. But most importantly, you must, before coming to the next class, it's a sincere request to all of you that please remember that Paul's exclusion principle, they are still not touched. They are still, they are still not violated rather. They are still intact. Whenever you will be filling the electrons in molecular orbital, you will be saying that pairing will start only when each one of the orbital of equal energy has received one electron each. So we'll be talking more about molecular orbital theory in the next class, and probably we will end this chapter with MOT then, right? So I'm sorry for the interruption we have in today's class. We will try to make it up in the next class, and we will do MOT. Please recall all your concepts of atomic orbital theories, right? So with that, should I end the class, or do you have any other queries, Ritika, Shweta, and Ananya?
No, ma'am.
No, ma'am.
Okay, thank you. Have a good day.
Thank you, ma'am.
Thank you, ma'am.
Welcome.